of finding the eigenvalues and eigenvectors, why do we take determinant of a minus lambda I is equal to 0? Why that determinant is 0? Give me your understanding. Dear students, hello. Students, am I audible?
Try to avoid trivial solution because we want a non-trivial solution.
Huh?
To avoid a trivial solution.
This is drawn from this solution of the equation, that homogeneous equation, a minus lambda I into x is equal to 0, right? So from this equation, how we can understood that determinant of a minus lambda I is equal to 0? That is my question. Why determinant of a minus lambda I is 0?
So because we want it to be non-invertible, and if it's invertible, that is x equals a minus lambda I inverse into 0, then we get a trivial solution.
So that is right. X is equal to 0. For the solution of this equation, a minus lambda I into x is equal to 0. Trivial solution x. Okay. But why determinant of a minus lambda I is equal to 0? That is my question.
Sir, this is a homogeneous equation, and where x is not equal to 0. So, sir, it has a non-trivial solution. So that's why a minus lambda I determinant is 0.
So for getting non-zero solutions, non-zero solution of x, when this non-zero solution could be achieved, obtained, if a non-homogeneous system, suppose if you take the homogeneous system Px is equal to 0, know what is the behavior of this homogeneous system when it has the non-trivial solution? For non-trivial solution, when it would be exist non-trivial solution, the rank of B, right, which should be less than n, right? What is n there?
Number of unknowns.
Right. So when rank, suppose B is of order n by n, B is of order n by n, square matrix of order n. So in such case, for getting that rank less than n for non-trivial solution, so the what is the largest order of the matrix? That is B of order n by n. So its determinant is equal to 0. If it is less than rank less than n means its determinant is equal to 0. Apply the concept of the rank of the matrix, right? How we define the rank of the matrix? Highest order non-zero minor, right? Highest
Yes,
order non-zero minor is called the rank of the matrix, where minor means the determinant of the square submatrix, right? So like that you find out the highest order submatrix of the matrix B, where the rank cannot be n, because maximum of the rank of B is n if it is of order n by n, right? rank less than n is required. So therefore, the largest minor is equal to 0. Largest minor means the matrix B itself. So where B may be considered that coefficient matrix A minus lambda is equal to 0. Understood? Clear?
Yes, sir. Yes, sir.
Right. Highest order, that means that may be determinant of minimum lower order minors, maybe n minus 1, n minus 2, whatever, that may be non-zero. That here it is not particularly specifying this much rank, but the rank is less than n. That means the highest order minor of order n is equal to 0. If rank less than n means nth order minor is 0. That is, nth order minor means the matrix itself. Right? So for finding the eigenvalue and eigenvector, we left x is the eigenvector and corresponding to the eigenvalue lambda, it satisfies the equation a minus lambda I into x is equal to 0. So the characteristic equation resulting u determinant of a minus lambda I is equal to 0. Finding the determinant of a minus lambda I, it resulting in a polynomial in lambda of degree n. If it is of the given matrix of order 3, square matrix of order 3, then the resultant characteristic equation is of order 3 only in lambda. Okay, so then its roots, this is called the characteristic equation. That characteristic equation roots are 3, 6, 9. Now find out the non-zero solution for each lambda. They are called the eigenvectors. Now for lambda 1 is equal to 3, first eigenvalue. Let x1 be the eigenvector corresponding to lambda 1. That vector may be considered. It will be of column vector. So therefore, with these 3 elements, because A is of order 3 by 3. So therefore, you take it in a vector of 3 elements, x1, y1, z1. So therefore, the solution is a minus lambda I into I, lambda 1 into I into x1 is equal to 0. So write down, it's a minus lambda I, 5 minus lambda 1 minus 2, 0, minus 2, 6 minus lambda 1 to 0, 2, 7 minus lambda 1 into x is x1, y1, z1 is equal to 0, 0. So now putting the lambda 1 is equal to 3, so you can get it like this, and we solve this system equation by reducing it to echelon form through performing the elementary row operations. It will give you, it's very clearly, it's surely giving you rank less than n. You know why rank less than n? Our assumption itself, this statement itself, it shows you the rank cannot be equal to the order of the matrix. So therefore, it should be less than n. So when less than n, here we can get it that rank. The rank of the matrix, coefficient matrix, it will be 2. Okay. So therefore, which is less than number of unknowns, where number of unknowns we have 3. So therefore, how many independent solutions are there? N minus r. Rank is r, is then number of unknowns n, then n minus r resulting you the independent solutions of the system. So where it resulting you 3 minus 2, one independent solution is exists. That one independent solution you maybe assume any of x1, y1, z1. I just consider z1 is equal to k as independent solution. So that from this transformed equation, you can write it the equation form 2x1 minus 2y1 plus 0 is equal to 0. One equation. Next, second equation, y1 plus 2z1 is equal to 0. It resulting in 2 equations, but we have 3 unknowns where we found one independent solution that we considered z1 is equal to k. Right? When z1 is equal to k, y1 can be determined from one of these equations. Y1 is equal to minus 2k. So from y1 and z1, we can get it x1 from the first equation. So that x1 is equal to minus 2k, right? So hence the required eigenvector for the eigenvalue lambda 1, x1 is equal to x1 y1 z1 minus 2k, where we take common 2. So therefore, it resulting you the independent vector minus 2, 1. So that's why we said that the eigenvector is not unique. You may take any value of k, it resulting you different eigenvector, right? You see, suppose k is equal to 1, this is minus 2, 1. K is equal to 2, it will be minus 4, 2. Like that, there will be several eigenvectors we can generate, but they are all our constant multiple of independent vector corresponding to the eigenvalue. So therefore, we may be considered that independent vector, that is minus 2, 1 is the required eigenvector corresponding to the eigenvalue lambda 1 is equal to 3 for the given matrix A, right? In the same way, we can get it for lambda 2 is equal to 6, second eigenvalue. For that also, you can get it the way follow for the eigenvector, that is 2, 1, 2. And similarly, for the third eigenvalue lambda 3 is equal to 9, we can get it that eigenvector x3 is equal to minus 1, 2, 2, right? Any doubt in this? This is where we have clearly calculated. So we can summarize that the eigenvalues and eigenvectors for the given matrix A, where the eigenvalues are 3, 6, 9, and the corresponding eigenvectors are x1, x2, x3. Right? I hope you have been known this one. Right? Now find out here one of the problem we can choose. Can you do this? Please do it. The first one I will give you here. Here we can observe that the repeated eigenvalue is being observed. That is 2 has multiplicity 2. 2 times repeated the eigenvalue 2. So how we can get the eigenvectors? The corresponding eigenvectors. There will be 2 eigenvectors. No, it is needed 2 eigenvectors for the same eigenvalue. We will look how it will be generated. How we can obtain the eigenvector for the repeated root. Okay. First, do this problem so that we can understand. This one is very easy. The same. There are distinct eigenvalues and distinct eigenvectors can be. So this is normal problem. This is where the eigenvalues are repeated so that we can get it in a way that to find the eigenvectors for repeated root, repeated eigenvalue. Check it. Find out what is the characteristic equation accordingly. Eigenvalues. Verify your calculation. Check. Find out the characteristic equation for the first problem. Hmm? The students? Hmm? Hello? The students doing?
Yes, sir.
Have you get this characteristic equation?
Yes, sir.
Right. Eigenvalues 2 to 8, right?
Yes, sir.
Go ahead and find out the eigenvector for lambda 1, that is as lambda 2 is equal to, right? Hello?
Done, sir.
Very good. So where you can see that for lambda 1 is equal to, can anybody say what are the eigenvectors obtained? Two eigenvectors or only one eigenvector?
Sir, 2.
Two. You see? So where the rank of A is 1, you get it, I think so.
Yes, sir.
Right. So therefore rank of the coefficient matrix is 1 means there should be two independent solutions, right?
Yes, sir.
Because number of unknowns are 3. So therefore 3 n minus are independent solutions. So therefore you considered two independent solutions from x1, y1 and z1. So I just considered y1 is equal to k1 and z1 is equal to k2. Understood?
Yes, sir.
So now from this solution, the transformed system, we can write in the equation form, that is 4x1 minus 2y1 plus 2z1 is equal to 0. Only single equation has been extracted. So therefore, from which we can write it, x1 is equal to this much. When we consider y1, z1 are two independent solutions, then x1 become 1 by 2 into k1 minus k2. So when x1 is equal to this much, so then the vector is x1, y1, z1, that is equal to this. You can separate that one. x1 in terms of k1, k2, y1 also you write in terms of k1, k2, and z1 also write in terms of k1, k2. Then you make it into two different things, right? That shows you here x1 is the linear combination of two vectors, two independent vectors, right?
Yes, sir.
So therefore, these two independent vectors that we can consider as the required eigenvectors for the corresponding eigenvalue lambda 2. Lambda is equal to 2 with multiplicity 2. Right. Understood? Here, any doubt in this?
No, sir.
Good. Now find the third one. Third one is as usual, you can obtain. Okay. Now, do you have any doubt in finding eigenvalues and eigenvectors?
No, sir.
So now see the next problem that we have to do it by Kelly-Hamilton theorem. What Kelly-Hamilton theorem states? What is the Kelly-Hamilton theorem? Remember, what is the Kelly-Hamilton theorem? Every square matrix every square matrix satisfies its own characteristic equation, right? Students,
Yes, sir.
you must be very keen about that one. So that is the first question here. Show that the matrix satisfies its characteristic equation. And also find out its inverse. You see, this is the characteristic equation. Determinant of A minus lambda I is equal to 0. What is the characteristic equation? Determinant of A minus lambda I is equal to 0. Right?
Right, sir.
Good. You there? Hmm? Check it whether it would be satisfied or not. It's characteristic equation. That means you have to show that this is the characteristic equation. That characteristic equation would be satisfied by A, the given matrix. So that means you have to show that A cube minus 13A square plus 54A minus 72 is equal to 0. Verify. Or check it whether it satisfies or not. If it is equal to 0, you can say that the Cayley-Hamilton theorem verified or the solution gets over. How you can find the A inverse? Next step. First do this one. Hmm?
Yes, sir. A is satisfying.
Yes, satisfying. Good. So now see, I think you can find out A inverse from that by operating multiplying A inverse on both sides of this equation where A satisfies. Okay, that means what is A inverse from this? You can write it directly. Multiply with A inverse on both sides. So it results in you A square minus 13A plus 54I is equal to 72 into A inverse, right? Now A inverse is equal to 1 by 72 into this much, right? You find out this one.
Yes,
1
sir.
A minus 13A plus 54I and divided by 1 by 75. This is the required A inverse. Okay? They're like that only, they will be simplified, simple questions are there. We can. Now can I give a problem on the diagonalization?
Yes, sir.
Right. Next problem. Can I go for the another? I think it is better to take a new one. I will let me close this. Problems on the diagonalization. Find a matrix P which transform the matrix A is equal to 1 0 minus 1 1 2 1 2 2 3 to diagonal matrix. Hence calculate A power 4. Okay, right? You have to diagonalize this matrix A. That diagonalization can be achieved by the model matrix P. The model matrix P can be obtained. How the model matrix P is obtained?
So your screen is not visible.
Oh my God. Oh, sorry, I haven't said. Okay, right. Right. Now see. Now it's okay.
Yes, sir.
I forgot. You see the question. Take it. So how that P would be found? What is P? How P would be constituted? Tell me how model matrix will be constituted? By eigenvectors, right? Independent eigenvectors.
Yes, sir.
Right. So therefore, it is needed to find out the eigenvalues and eigenvectors for the given matrix. The given A is equal to 1, 0, minus 1, 1, 2, 1, 2, 2, 3. Find out its characteristic equation. Is determinant of A minus lambda I is equal to 0. Right? For eigenvalues and eigenvector, let lambda be a scalar. If there exists a non-zero solution x such that Ax is equal to lambda x, then x is called the eigenvector corresponding to eigenvalue lambda, right? That means it resulting you A minus lambda I into x is equal to 0. Say 1. Its characteristic equation is determinant of A minus lambda I is equal to 0. What is its characteristic equation? Can anybody find out? Lambda cube minus 6 lambda square plus 11 lambda minus 6 is equal to 0. So you know that is, it has the roots 1, 2, 3, right? This is a characteristic equation and the eigenvalues. Lambda is equal to 1, 2, 3. Right? They are distinct eigenvalues and the corresponding eigenvectors. Vectors x1 is equal to 1 minus 1, 0. Right? You can find out them. I think it is very easy. You know that process, right? Minus 2, 1, 2. For lambda is equal to 3, x3 is equal to minus 1, 1, 2. Okay? Right? Any doubt in this?
No, sir.
You can find out the eigenvalues and eigenvectors. Now, the model matrix P is constituted. Now, the model matrix P is constituted by the eigenvectors. Therefore, P is equal to x1, x2, x3. That is equal to what is x1? 1 minus 1, 0. x2 minus 2, 1, 2. Minus 1, 1, 2. Right? This is matrix P. Matrix P. Now, find out its P inverse. P inverse is equal to, you know that 1 by det A into adjoint A, that is 0, 2 minus 1, 2, 2, 0, minus 2 minus 2 minus 1. You can get it, this P inverse. Okay, so now how we can diagonalize the matrix A? How we can diagonalize the matrix A?
So P inverse AP.
Very good. P inverse AP. You find out now. Now you find out this P inverse AP and show that is equal to the diagonal matrix with the all principal diagonals or the eigenvalues. Then we can say that P is diagonalized the matrix A. There P and there A and D diagonal matrix D are similar. To find out P inverse AP, hmm? Hello. So slowly find out that. Hmm? Have you calculated the P inverse AP, friends? Hmm?
Yes, sir.
That is equal to, I hope, 100,020,003, right? P inverse into A into P, you have to find out. I will write it here. How it is. P inverse is minus 1 by 2 into minus 1 by 2 into 0, 2 minus 1, 2, 2, 0, minus 2 minus 2 minus 1 into A. A matrix is what? What is A matrix? 1, 0, minus 1, 1, 2, 1,
2, 2, 2.
2, 2, 3.
2.
2 to 3 now. 2 to 3. P inverse A, P. P matrix is this one. 1 minus 2 minus 1 minus 1 1 1 0 2 2. You just multiply with that, it resulting U. It's very clear. 1 0 0 0 2 0 0 0 3. That is D na diagonal matrix of lambda 1 comma lambda 2 lambda 3, right? So hence P diagonalized. P is called the spectral D is called the spectral matrix, P is called the model matrix, right? Now find out A power 4. How we can find? We know that finding power, finding A power 4. We have A power n is equal to, same from this only, A power, that means P inverse AP is equal to D. We have that, we can rewrite into that A power n is equal to P into D power n into P inverse, right? Since we have P inverse AP is equal to D and D power n is equal to P inverse A power n into P, or A power n is equal to, you pre-multiply with P for T. T power n post multiply with P inverse. Right? A power n is equal to P into D power n into P inverse. You know that P is 1 minus 2 minus 1 minus 1 1 1 0 2 2. So now that implies A power 4 is equal to, putting n is equal to 4. A power 4 is equal to P into D power 4 into P inverse. Into D power 4 is, what is D power 4? 1 power 4 0 0 0 2 power
2 power 4 0 0 0 3 power 4
4 into P inverse minus 1 by 2 into 0 2 minus 1 2 2 0 minus 2 minus 2 minus 1. Okay, you multiply this one, it results in you the required A power 4. So hence A power 4 is equal to, I am giving you can verify that it is minus 49 minus 50 minus 40 65 66 40 130 130 81. Right? Like that we can obtain the power of the matrix through the diagonalization. Right?
Sir, this A power 4 can be found also through Carey-Hamilton method also.
Like that also you can carry it, but there itself it is needed A square like that, no? Right? In Kelly-Hamilton theorem, you have to, suppose if you apply the Kelly-Hamilton theorem, there itself, there here, that A satisfies this equation. That means you have been obtained A cube minus 6A square plus 11A minus 6I is equal to 0, right?
Yes, sir. Yes, sir.
By Kelly-Hamilton theorem. So you can get it this one. Now from this, how we can find out A power 4? First multiply with A on both sides.
Yes, sir. Yes, sir.
First multiply with A on both sides. So therefore, and A4 is equal, A power 4 is equal to 6A cube minus 11A square plus 6A, right?
Right, sir.
This is A power 4, but you needed A cube, A square and all. If there is any higher power, it's needed the lower powers in the Kelly-Hamilton theorem, right?
Yes, sir.
But in the diagonalization, it is not needed, just only three matrix multiplication, P into D power n into P inverse. It is very helpful. The diagonalization concept is helpful for finding the power of n, and it also can easily programmed. It also can easily program in the computer. Using computer, we can easily to get it. Right?
Okay, sir. Got it.
Any doubts?
No, sir.
Thank you.
Thank you, sir.
Thank you.